So in the next problem, we are going to have the orthocenter of the triangle PQR, where PQR are the normals, the feet of the normals, so that the normals at them meet at HK. So for that, we first write out the relation between the roots and coefficients by considering the parametric form of equation of normal. And because it passes through HK, we have these set of equations. And our aim is to find the orthocenter. By the definition, orthocenter is nothing but the meeting point of the altitudes. So to get the equation of the altitude, say if you consider this one RQ, for which PM is the altitude, and for PQ it is RL as the altitude. So we have to get the equations of them, for which we are going to use the technique that if we know the slope and the point on it, we can easily write out the equation. So it is that we are going to use. So to get first the equation of LR, point is known, slope we have to determine. But the equation of the chord joining P and Q, from which we can easily get the slope to be this equation of the line joining P and Q. I mean the chord joining P and Q is nothing but y t1 plus t2 is equal to 2 into x plus a t1 t2. So from this, the slope is obviously 2 by t1 plus t2. For the perpendicular, this is the slope. So we know slope and a point, so we can easily write out the equation of RL or LR. So that is written. In the same way, PM is written. So that is this. Our aim is to solve these two. That means we have to get the value of x and y. So subtracting 7 from 6, this is what we have. Now in this, if you look at the second term alone is written here. After subtracting, this is what the second term is. So you have t1 plus t2 by 2, t1 plus t2 by 2 a into t3 square. We have taken a by 2 out. So t1 plus t2 t3 square minus a by 2 is taken out. So t3 plus t2 t1 square. Now we consider this one t1 t3 square. In that t1 t3 we are taking out. So we are left with t3. And from here t3 t1 square, t3 t1 is taken out. We are left with t1. So this is what we have. And as for the second one is concerned, t2 is common. So t2 is taken out. What's remaining is t3 square minus t1 square. But then that is rewritten as, because it's of the form a square minus b square. So a minus b, a plus b. So that is what is written here. So now we can cancel this t1 minus t3, that's common throughout, that can be cancelled. And so we are left with only this term. Minus 2a is equal to x by 2 plus a by 2 into sum of the product of the roots taken 2 at a time. And that from the relation 4 is nothing but 2a minus h by a. Now we can cancel this a, and this on simplification will give us x to be h minus 6a. We can cancel the terms and simplify the terms, and ultimately we get x as this. Now we are going to use the value of x in either 6 or 7 by using that in equation 6. This is what we have. We are replacing x by x h minus 6a. So then t1 plus t2 plus t3 being 0, we can have this as just t3. Minus of t1 plus t2 is t3. So this is what we have, and then t3 is taken out, 2a, the remaining terms, and then that is simplified further. And this is what we have. Now from this, this minus a by 2, when minus a by 2 is taken out, when minus a by 2 is, or rather minus half is enough, minus half is taken out, this is what we have, 2a minus h, this t3 is taken inside. So this becomes 83 cube. Now if you look at the equation of the normal at t, this is the equation 280 plus 80 cube, but uh, at T3 means this is what we have, and because it passes through HK, this is what we have. So from here, K is nothing but this, and that is the term that we have here. So that is replaced by K. So if we name this as star, using star, we have this. So we have the y coordinate to be minus K by 2. So x coordinate already is h minus 6a. Now that we have y coordinate to be minus K by 2. Now in the following 2 or 3 problems, we are going to consider the point of intersection of the normals drawn at 2 different points of contact, namely P of T1 and Q of T2. So this is the point of intersection of the normal that is to be remembered. The x coordinate is 2a plus a into T1 square plus T2 square plus T1 T2, and that is obtained by just solving this y plus xt1 2at1 plus at1 cube, and similarly y plus at t2. We'll have to solve these two to get the coordinates. So these are the x and y coordinates, and using this only some of the problems can be easily dealt. That has to be remembered. The point of intersection of the normals. Now what is the problem? We are asked to find the locus of point of intersection of two perpendicular normals to the parabola. Two perpendicular normals. We are considering normals at T1 and at T2. Say what is known about the normal is they are at right angles. That means the slope of if you consider the slope of this and the slope of this, product of the slope is minus 1. So when we consider this equation, obviously the slope is minus T1 and the slope of this is minus T1, this is minus T2. So product of the slopes means we have T1 T2 that is equal to minus 1. So with this condition, because whenever we are asked to find the locus of any point, some condition needs to be given. So here the condition is the normals intersect at right angles. That is, they intersect perpendicularly, and therefore we have T1 T2 is equal to minus 1. Now already we have the relation. See the locus of point of intersection. Point of intersection we know. So locus of that point of intersection is needed. So we shall take that point to be x1, y1. Point of intersection. Only then by dropping the suffix of this we get the locus. So x1 is taken as the x coordinate, y1 is taken as this. And remember in this we have T1, T2 is equal to minus 1. Right. Now we have using this in equation 2. So T1 plus T2 can be replaced, T1 T2 is replaced by minus 1. So y1 is equal to T1 plus T2 into A, or in other words T1 plus T2 is y1 by A. Now going to equation 1, x1 is 2a plus a into, we can rewrite this T1 square plus T2 square by adding and subtracting 2 times T1 T2, so that this and this gives us T1 plus T2 the whole square, and here minus 2 T1 T2, and there it is just T1 T2. So ultimately we have minus T1 T2. So this is what we have, and T1 plus T2 can be replaced by y1 by a. So we have this. So in this we have x1, y1 and the known terms. So further simplifying and dropping the suffix will give the required locus. So we have this to be x1 this is a, so 3a, x1 minus 3a, into this one a square you have in here a. So one a can be cancelled and then cross multiplying. This is what we have. So we want to find only the locus of point of intersection. So you have that to be x minus 3a equal to y square. Now the next one is find the locus of point of intersection of normals at the ends of a focal chord. So here again locus of point of intersection of the normals only. As before we'll have to consider the point of intersection of the normals at t1 and t2, and they are taken as x1 y1 as before we have this. But remember, whenever we have to find the locus of any point, some condition needs to be given. So here the condition given is the locus of point of normals at the ends of a focal chord. Normals at the ends of a focal chord. So if we consider this one, the we have that point t1 and t2. We are asked to find the locus of point of intersection of the normals at t1 and t2. What is known as the normals are at the ends of a focal chord. So focal chord, we have this a0. We know the equation of the line joining t1 and t2. Y into t1 plus t2, this one. Y into t1 plus t2 is equal to 2 into x plus at1 t2. But because it passes through a comma 0, replace your x by 0. So you have your y is a t1 plus t2 is equal to 2a into t1 t2. So this is what we have. Okay, so because the equation of the chord joining P and Q is this, and it passes through the focus a comma 0, which means y is 0. Which means y is 0, not x is 0. Y is 0. So you have 0 equal to 2 times a plus 2a t1 t2. So cancelling out this 2a, we are left with t1 t2 is equal to minus 1. So in the same condition only we also had in the previous case, but the wordings were different, and here the wordings are different, but the condition that t1 t2 is equal to minus 1 is the same. So which means we'll have to proceed as in the previous problem, so that we can have our relation between x1 y1 in terms of known constants as the same as the previous one. Dropping the suffix, we get the locus. Now the next one is the chord PQ of a parabola subtends a right angle at the vertex. What is the locus of the point of intersection of the normals at P and Q? So we have the normal at P and Q intersecting at some point, say x1 y1, the locus of which is asked. Okay, so we have as before x1 being taken as this, y1 is being taken as this. Now in the previous case and all, we had t1 t2 is equal to minus 1 with the condition given. In this case we are going to have this t1 t2 as minus 4. How is it? So for that, you look at the condition given. The chord PQ subtends a right angle at the vertex. So we have the chord PQ. What is the chord PQ? Here we have the normal at P intersecting at the point, say some T, PQ. This chord PQ, this one subtends a right angle at the vertex, which means OP, the slope of OP into slope of OQ should be minus 1. Now how to get the slope of OP? It is at1 square 2at1. So difference between y coordinates, what is it? 2at1 minus 0 divided by at1 square minus 0. So you can cancel 1a, 1 t1 can be cancelled, 2 by t1. So the slope of this is 2 by t1. The same way slope of this is 2 by t2. But what is known about them? 2 by t1 into 2 by t2 should be equal to minus 1. So this in turn gives t1 t2 is equal to minus 4. In the previous two problems we had t1 t2 to be equal to minus 1, whereas here it is minus 4. Technique again is the same. We have t1 square plus t2 square means completing the square. That is the technique used here. And you'll have to substitute what is your t1 plus t2, and that comes from here. So you have t1 t2 to be minus 4, so y1 becomes 4a into t1 plus t2, and therefore t1 plus t2 is y1 by 4a. So we'll have to just complete the square and use this value. After simplification, dropping the suffix, we get the locus. So in the next we will have conormal points of an ellipse.